All right, let's take a look at what a Cauchy sequence is. A sequence, S of n, of real numbers, it is a Cauchy sequence. If for every single epsilon there exists a natural number n, such that whenever both m and n and little n are greater than big N, this should imply that the distance between those two terms in the sequence is going to be less than epsilon. Right? So it is Cauchy if after a certain point the space between any other two terms in that sequence is less than epsilon. And no matter what choice of epsilon you choose, you can always define what it means to be far enough in the sequence so that any two terms that are far enough along in the sequence will be guaranteed to be less than epsilon units away from each other. All right, so let's look at some examples. We won't formally prove these, but we'll just try to build some intuition a little bit about some Cauchy sequences. All right, so here, let's see if we can build some intuition on trying to decide whether or not something is Cauchy or not. Right, so here we have our sequence. S of n is 1 over n. And so if we wanted to look at the absolute value of the 10th term in the sequence, which would be 1/10, minus the 5th term in the sequence, 1/5, that absolute value is 0.1. If we were to look at the 50th term minus the 45th term, the distance between the 50th term in the sequence and the 45th term in the sequence, we're going to get something that's like 0.0022. Right, so that would be 1 over 50 minus 1 over 45. If we go the distance between the 100th term and the 95th term, we're going to get something like 0.0005. Right, so that's the space between those two values. And as we keep going further along in the sequence, the distance between terms is going to continue to get smaller and smaller. And so this does turn out to be a Cauchy sequence. You can choose an epsilon, and for every single epsilon that you might choose, you could then define what it means to be far enough along in that sequence that would force any terms in the sequence past that point to be within epsilon units of each other. All right, so let's look at our next example here. And so in this next example, we have 2 plus 1 over n whenever n is even, and negative 2 minus 1 over n whenever n is odd. And so the difference between our 10th term and our 5th term is going to be something like 4.3. The difference between our 50th term in this sequence and the 45th term in the sequence is something like 4.042. Distance between our 100th term and our 95th term is 4.0205. This is not Cauchy because the space between these is going to possibly get smaller, although maybe that's not really quite true. But there will always be, no matter what you might define big N to be, there's always going to be two terms in your sequence further down the line that are at least 4 units apart. So you're never going to be able to have, say, if we get far enough, every term far enough in the sequence is going to be less than half a unit apart, or 1/10. We could never define epsilon to be 1/2 or 1/10 and force and find a value of n that would satisfy every term after that is within 1/2 or 1/10 of a distance between them. What about our next sequence where we have 5n minus 2 over n plus 4? So when we look here, we have something like the distance between our 10th term and our 5th term. I get something like 0.873. Distance between our 50th term and our 45th term, we get 0.042. The distance between our 100th term and our 95th term is 0.011. Turns out that this sequence, yes, it is also Cauchy. As we keep going down this sequence, our terms are going to all keep getting closer and closer together, and that distance between them is going to head towards 0. So that is a Cauchy sequence. For the sine of n, we have the distance between the 10th term and the 5th term is 0.451. 415 rather. The distance between the 50th and 45th term is 1.11. Between the 100th term and the 95th term, we get something close to 1.18. This is not a Cauchy sequence either. These are looking like points that are on a sine graph, right? And so if we're looking at points on a sine graph, these points on a sine graph, they are going to sometimes be really close, and sometimes they might be really far away. Really far being like up to a distance of 2 away. But we can't guarantee that everything is going to be less than epsilon past a certain point. All right, we'll go through 1 or 2 more of these examples, and then I'll let you guys try the others on your own. All right, so let's take a look here. So we have 3 minus e to the negative n whenever n is even, and it's just 3 whenever n is odd. So here we get 0.0000045. So something pretty close to 0. After this, it's actually getting even closer to 0. It's not actually 0, but it's really, really close to 0. It turns out that, yes, this is Cauchy. These terms, once we get far enough along in the sequence, all the terms are really, really close to 3, and they're just going to either keep getting closer and closer to 3 or be 3 exactly. Every other term will be exactly 3, and then all of the even terms are going to just keep getting closer and closer to 3. So we can get far enough along in the sequence that they're all going to be close enough. And then this last example here, we have like 0.3, 0.042. Then we have 0.0205 is the distance between the 100th term and the 95th term. The space here between terms after a certain point, it is heading towards 0, and so this is a Cauchy sequence. So you can take some time to go through those other examples and see if you can build your intuition about Cauchy sequences a little bit more. So now that we know what a Cauchy sequence is, in the next video we will talk about other things that we can prove to be true based on Cauchy sequences. Thanks for taking time to watch the video. We'll talk to you guys later.